So hey folks, thanks for joining us for this session today. So this is Jens Reimann and I'm Dejan. We're coming from the Red Hat, from the messaging and IoT teams within the middleware group, trying to focus on the messaging and the IoT use cases within the group. So, how much of you guys have heard about Hono, played with it, and tested it? Okay, fair amount. So let's give a brief recap.
One question: who's not from Bosch and has played with Hono?
Okay, couple of folks. But generally, the general idea and the promise of Hono was to always to provide a cloud scalable IoT connectivity for IoT, right? So for that we need to provide two things. Basically, we need to provide a general purpose scalable messaging system that will run underneath, and the Hono components themselves needs to be very scalable. So when we talk about particular use cases that Hono tries to do is it tries to provide well-structured APIs for developers they can use to particularly target IoT use cases like sending telemetry data, sending commands to the devices, and all that to be able to scale to the cloud level scalability that would we expect. So from the day one, we said we need to make a scalable platform. So allow a large number of devices to be connected, millions, to allow a high volume of messages, telemetry messages, to be ingested into the Hono. So the whole architecture was designed on top of those premises, right? So very simplified architecture that's going into the Hono is that we have devices on one side. We have some of the Hono components like protocol adapters and device registries. We have the general purpose AMQP messaging infrastructure, and then we have consumers on the other side taking that telemetry data. So what we try to do, and so we claim this, but we want to test this and put this claim to the test to see like if we really can achieve scalability that we would expect, right? And testing these kind of things can be tricky because you need a lot of resources, as we will see, and dedicate the cluster to achieve such a test. So maybe Jens can take over and
I will take over and stop me when I say something wrong. So this is not the first time we tried to test Hono. So we did go along in late 2017. Actually, that was like a little bit by accident. There were a few resources left over from other scale test, and we were offered like a few resources which we could like play around with. So we had a first attempt to run the largest test, which means like you take the whole stuff outside of your local laptop, out of your local development environment, and you put it to something more productive, to a more productive setup. So the first try actually was we failed miserably. We didn't. I think we had also like a short amount of time only, so it was a little bit rushing into that. But it didn't really work out. So because of multiple reasons, I don't really want to go into that.
But then, of course, simple reason is that for the limited time, setting up the cluster like this of this size takes a lot of time. So a couple of days just to get it basic. I mean, depending on what you have at hand, it can take a lot of time, and then
stories from the scale test. You set something up, it doesn't work, and you figure out it's a broken disk. So this is the stuff we run. So we made like to the whole Hono deployment for the OpenShift part. We made several improvements on like how we want to tackle those problems. And so in early 2018 we made a second test actually this time applying for our own cluster and trying to validate if those fixes that we did actually work. So we had some assumptions, we tried that, and yes, we were able to get that up and running. But we also learned, like, again, with every test you learn more and more. So we learned a little bit more, and I think it was clear that at some point we want to replicate that. And so yes, we went for July 2018. We started another test, and we went with the current development version of Hono. Also, like trying to validate the same setup with the version from January 2018. But again, Hono 07. What we see later. That's what we wanted to do. So
one more thing that we forgot to mention is that we were for the moment being focused on only one of the use cases of Hono, so running it on the OpenShift cluster and running only telemetry payload there. So there's a multiple APIs of telemetry, events, command and control. So we wanted to start with the first one we developed actually. So let's start with scale testing that was the focus of this effort.
Yeah. So just so you get a little bit of idea what the lab was looking like. We are in a lucky position that we have multiple labs where we can pick resources from. One lab which we already knew from past tests was exactly that. We'll see on the left-hand side. This is the full lab capability that we had, or where we could pick resources from. So you don't get anything. Usually you don't get everything. You make a reservation for some of this. And so this is what we, on the right-hand side, what we basically picked. So it's like 16 servers, RAM, cores, whatever. And the initial plan was to do it for 3 weeks. And we already assumed that 1 week will just be wasted for setting up the operating system, setting up the cluster, setting up RAID disks, stuff like that. And that was a fair estimate, and it worked exactly out that way. Yeah. And then we extended it in the end, so there was an option to extend that to test further events. So we had the whole setup done, we had the chance to extend this for 1 more week, so we could look into event testing beside what we did telemetry testing. So this is the basic setup that we made. So we had a plan of splitting this up into 2 clusters. One for running Hono itself, which would be like the setup of, this is how you set it up, and now you throw all your IoT devices against that. And this is like the blue part, where we have 12 nodes in there. We had a dedicated master node, because what you normally do on your laptop, you set everything up in one big machine. That's not how you would deploy it. You would have at least one master. You most likely would have multiple masters for redundancy. You also do have infrastructure nodes. So these are nodes where, for example, HTTP traffic will be processed and then distributed to the different services on those compute nodes. So we had those 8 compute nodes, and they were running the Hono components, Hono services, NMAS services, all those things that you need. And then we have the green cluster. The green cluster again is single dedicated master setup, and we had 3 compute nodes which are running the simulators. So one question is, of course, so why do we have a green cluster? So why do we use OpenShift for that as well? There's no real need to do that, but it was pretty convenient. So you have all the build tools, you have all these the easy orchestration of the containers of the simulator. You can easily scale up or ramp up the producers and the consumers, and you can automate that. So you write a small application which like fires up more and more producers. So it was just a convenience, but it's not a necessity. So this was, as Dan already mentioned, the main focus of our test, telemetry. We wanted to do that and focusing on HTTP as a first use case. There are so many different things that you can test, but if you really want to focus and like repeat tests over and over again, it makes sense to like first pick one use case and just go for that. So, as I mentioned before, we later also tested events, and we tested MQTT, and we tested all the different other kind of variations. But this was the main test that we did. And so if you have a look at the Hono components involved, or the messaging components involved, this is mainly the HTTP adapter. It's the Qpid router from NMAS, which is distributing the messages to the consumers. And then you have, of course, simulating devices and simulating consumers. So let's have a look at the software components that were involved. Of course, if you invest 4 weeks of testing and resources from a bigger cluster, there is some interest from your managers to actually get the productized version of different components tested. So we went with the supported version of OpenShift. We went with RHEL instead of CentOS. And we used NMAS 021 for the messaging layer. On the Hono side, we used 07. It was a snapshot close to M2. So what we did is we forked the repository and added a few fixes ourselves, what was required during the test. And this is also available on GitHub, so there's nothing like we hide that and that's now somewhere hidden with some magic sauce. No, it's available on GitHub, and if you want to try out the same scale test, you can actually use the exact same branch. You see the down below here, the lower one, this Hono scale test repository, that's actually the setup that we did, including the OpenShift setup and how we deployed the services, a little bit of documentation around that. So again, if you're interested, have a look at this, replicate what we did. And then we have in the middle the Hono simulator, which is basically a nice way to simulate IoT devices, which is a little bit if you want to test the throughput for IoT, I think it's worth mentioning that you don't have one producer which pushes as fast as it can, but you have a whole load of devices, multiple devices with multiple connections, publishing at a lower rate. But these are all tweaks that you can make to the simulation setup, where you can say, okay, I want to have this and that many devices simulated, and the frequency of the messages and so on. So, make a good plan and then fail miserably? No. The first thing is that we wanted to do this, as I mentioned before, we were really planning on having a single week setting up the whole cluster. And so you have 60 machines, they all look different. It's this is coming from a shared test resource lab. So someone sets up something, then its period is over, and you just inherit the legacy from the guys before. So yeah, repartitioning disks, stuff like that. This is fun stuff. Next thing, we wanted to create a baseline for testing. So we have this cluster, and you can set all those complex microservice stuff and messaging and distributed system. You can set up in multiple ways. So we want to figure out what's the best way, how can we achieve the best throughput, and so that we have a baseline which we can in the past in the time after that we can compare to that and see if this is improving things or making that worse. One plan also was to start automated testing, so not only to sit there and tweak the system and look how it behaves, but also to run a scenario, come back at the afternoon and look what came up. And then of course
the system can auto-scale it.
Yeah, so basically it's it's a more controlled way of auto-scaling, so that you also record at which time you scale up, and you have the metrics for scaling up, why do you scale up, what will happen if you cannot scale out anymore, so you abort the test, things like that. We also wanted to test a few scenarios. For example, Benjamin suggested to test OpenJ9. So is there any difference using OpenJ9? If you have a baseline, you have a test, you can swap the JVM and then look if that makes changes. Kai actually suggested to use different threading settings, and I was like, oh, this is no. Yeah, it's pretty interesting. It's really that was it's worth another test, I would say. Yeah, there's events. Command and control was like a little bit on the horizon then, so we didn't really plan for that. If there would have been time, we would add it as well. But pretty sure there's a next test coming up at some point. So up and running, just a quick look. You want to have an overview of a cluster. You want to just see what the current state is with like one view at the monitor at the screen. Turns out it's pretty hard because 16 clusters, it's already just to get the information shown in a nice way can be troubling. So we need a bigger screen. Just to compare that, it's like the one screen is like already a big screen, and so luckily we had a little bit bigger screens like that, just showing the cluster infrastructure. But it really helped just to have with one view to see where the problems are. Network problems, like we had, for example, one thing where we had down on those machines, and you do know which machines host which services. So we had network storage on there using Cluster, using a broker for events testing. And suddenly you see like spikes going up, and then you figure out, okay, that setting of network storage, that was a bad idea. So you can easily revert that and try next setting. So as I mentioned before, maxing it out was the first idea. So let's see what the cluster can handle. What's like the rooftop that we hit. And this is really important. So we're showing you a few numbers later on, and they may be completely different in your environment. So this depends on, I don't know, what CPU you have. Do you have the micro patch update for the CPU, which spectral meltdowns, like reducing that performance? It's like completely different results if you test this. So I would really encourage you to do your own tests. So if you want to figure out if it scales, how good it performs for you, then go ahead. It's all open source. You can replicate that. You can set it up locally. Gain lots of experience, and you can find out for yourself. So, measuring performance, what was our approach in doing that? So, how do we figure out if this is performing as expected or not? So, we had a simulation cluster, and the simulation cluster runs X pods, so we can scale up the pods to create more load. And they were simulating Y devices, so every pod was simulating, for example, 1,000 devices. And then we can go up and scale up one pod more, so we have 2,000. And every device is programmed to send one message each second, with a little bit of jitter in there, so it's not at every second like 1,000 messages, but it's like a little jitter in there. So that is the producer side. And then we record, in a time series database, we record the attempts to send. Very important, we see that later. So it's not only that when you're doing the test like that, that the backend scales, but also your test has to scale. So you're simulating 1,000 devices, but can your simulator handle that? So that was like the indication, okay, actually has the simulator tried to send? So you can check that. The simulation cluster also runs a number of pods consuming messages. So on the consuming side, we didn't throttle, we just consumed as fast as possible. Also recording how many messages were received in a time span. Then Hono handles backpressure by rejecting messages at the protocol adapter level. For HTTP, we have an actual code for indicating that. There are different error codes, different HTTP codes. So we also recorded which errors popped up in the test. So that we have like a metric of, okay, you have like 403 or whatever comes up. So it's a different problem there, maybe some other issue. What we then did is, like, if you have the attempts to send, you have the successful calls to the HTTP adapter, and you have the messages received coming back through the whole stack. Then you can calculate an error rate, where you say, okay, like expected this and this many messages going in, so many were rejected because of whatever, so many were lost, which like shouldn't be the case. But you have an error rate, and you can like figure out if the cluster still can handle the load you're currently throwing at. And then we can scale up the producers, the consumers, the infrastructure components. We can play around with that, and so we can see how the whole cluster is operating. And this is just one of the dashboards that we have, so that you get an idea what we did. So you can see on the upper level, this is the producing side. So you have the white line is actually the attempts to send. As you can see, I think it's like 2,000 messages, and then we scale up one part. So we have 2,000 messages per second more. You see a light red spike up there, which is like caused to, I don't know, some load which currently the system couldn't handle. So you get like feedback that okay, there you have failed messages. And then you see here on the middle row, you see the messages received. There's like a more accurate one and a moving average, just to smoothen that a little bit. And here you can see, so first thing we did, we scaled up one, and then we scaled up another 2 parts, and there you see like suddenly a different behavior. It's like getting a little bit more jitterish. The round trip time like increases a little bit. This is the round trip time. Still, the cluster can handle this because there's no error, so there's no problem. But still, you see like a different behavior in what is coming along. Again, one of those spreadsheets filling out testing for maxing that out, which like tweaks you can make. What's the best setup? How do you like approach that? What helps improving the performance? Well, this is the interesting rows, like how many messages per instance of a protocol adapter can the system handle? The failure ratio to ensure that this is below a certain threshold. Because there will always be at least one message missing or 2 messages missing, but what's the accepted minimum? And also, just to be sure, missing message is like more like a rejected message. So Hono has a concept for that. It rejects the message, so the device has to retry at a later time. But if it's like an accepted message, then it's like for the device, it's like okay, I don't need to care anymore. It's like an accept. So this is what we came up with in this specific cluster for our specific setup, a maximum of around 80,000 messages per second. We were running two dedicated QPID routers. So QPID is coming from the Apache QPID project, which is the router only forwards messages. It doesn't store the messages, and this is used for telemetry data. We had 2 dedicated QPID router nodes, so they were running on the infrastructure nodes of the OpenShift cluster. We had the device registry as a sidecar, and what that means, so as a sidecar means that you have, in the Kubernetes world, you have containers, which is a single process. You have a pod, which is a container or a group of containers. And you can actually have multiple processes, like multiple containers in a single pod. If you kill the pod, all containers will be shut down and fired up at a different location. So what we did is we put the registry as a sidecar next to the protocol adapter, and I explain in a second why. We had 8 nodes running Hono services, which from the picture before. We had to pick an HTTP library that scales, which was like a bit of a problem at the beginning. That's also like a lesson learned and solved and fixed. And what we found out is that the throughput is mostly limited by CPU and network resources. So RAM is not a limiting factor. So if you remember from the beginning that machines with 64 gigabyte of RAM and more, in this whole setup RAM wasn't the limiting factor. And neither was the disk or network storage for telemetry. So for events it's different, but please remember we were focusing on telemetry. So, a few things we learned. Device registry as a sidecar. So this is the very basic message flow for Hono. So you have devices, they send to some protocol adapter, and those messages, they will be forwarded to the QPID router for consuming by other applications. One step in the middle, is the adapter has to verify the device. So is that an authenticated device? Does it have permission? So there's, when a message comes in, especially for HTTP, so for MQTT you have more long-lived connections, but for HTTP you have short-lived connections. So the adapter has to check and recheck in the device registry if like you can go for that. And this might decrease performance. So if the device registry doesn't scale, your whole system will not scale. And what we wanted to take out of the equation was simply, we didn't want to check a device registry, so does that scale, but we wanted to check if the Hono system itself scales. So what we did is we moved the device registry from a single service, we moved that side by side with the container of the protocol adapter. That still leaves the communication between those two processes intact, so still the microservice is being communicated with, but it has no impact on the network, so on the real network in the cluster, there's no performance impact from that. Of course, in a real world scenario, you cannot just do that in that way, so you need to like take the device registry under consideration, and you need something that scales as well there.
One more thing we did for the device registry is we implemented the dummy device registry, because as Jens mentioned, so the point of this whole exercise was to check the scalability of the Hono main flow of the messages, so Hono components and the NMAS together. So device registry is something that it's, for now, it's not like official part, production part of Hono at the moment, so we wanted it to, for the moment, get it out of the equation. So we created a dummy one which always returns true to everything, so it doesn't have to do anything with...
So it doesn't impact anything, but still it is in the process of being communicated with, so it's not completely left out, and there's a Java function returning true. Communication is there, but the device registry not. So also what I mentioned before, so we put the Qubit router nodes, we put them on the infrastructure nodes. This helped to shape the traffic, so you don't have like nodes communicating with each other over and over again, blocking the network, but it's a more streamlined approach of messages flowing in and flowing to the next layer and then to the next layer. And then the quick overview of Java HTTP clients. So in the beginning we were starting with OK HTTP, which has a nice API, which is good performance. So, but at some point, if you start scaling up the simulator, we saw in this white line, you remember, it couldn't keep up. So we had to look at this, and it looks like internally OK HTTP is pretty synchronous. So it offers an asynchronous API, but that's just like yeah. So next thing to try is the Java default HTTP client. Completely sucks. Forget about that. Apache HTTP client is like again super complicated and not that performant. Then I ran over HAC, which is asynchronous HTTP client based on Netty. It has a very good performance, but the API is a little bit more like yeah, okay. And then there's Vertex, the Vertex HTTP client. So for Hono we're using Vertex already, so it was like yeah, why did we go for that? Good API, very intuitive, and an awesome performance. So we went with Vertex.
Yeah, one thing you always need to take care about when you're writing scale testing is how do you scale the simulators and the client, because usually client libraries scale much worse than the software stack. So it does need to be taken care of.
Unless you want to buy a million devices and ship that all the world.
Yeah. or turn things around, have a small server cluster and a huge simulator cluster.
So, lesson learned, native sockets and TLS. So Java has a little bit of problems when it comes scaling with TLS if you do it in the JVM. There was one reported bug towards the Hono project. We tried to verify that. The solution works. Again, EPOL is a better way of doing asynchronous I/O on the Linux kernel. So there needs to be native support for that. We added that to the whole setup, and like you can see a little bit on the right side. This is the point where we deployed, or where we enabled the EPOL implementation, and that like completely smoothens the message flow. Automated scaling tests. This is how we did it. One producer up. If the error rate is below 2% for a while, then we scale up the next producer. And we go on that way until we hit the limit of the cluster. At some point, the error rate will increase. Then we scale up a new HTTP protocol adapter. If we still have resources in the cluster, if we run out of resources, test is finished. It's very, very basic flow. And this is one of the results. So default scenario, this is how it scales. So you can see the green line, this is the number of simulated pods, like adding one on top of that. This like pinkish line, whatever, reddish line, this is the number of adapter pods which are required to successfully process in those error parameters this number of increasing producers. And then we have the round trip time. So the yellow line is the round trip time. So you see in the beginning it's like pretty low, then it's like getting in shape, distributing the load over the whole cluster. And there's like a spike here and spike there, but in general, like see on the left side we have the number of milliseconds for the round trip time delivering that message to the Hono protocol adapter. And then we have the messages per instance, messages per second per instance. So we have the number of
the protocol.
Yeah, exactly. So the number of protocol adapters, the number of messages. So that actually means what one protocol adapter instance can handle messages per second. And if you see this line here, it's like in the beginning, it's like okay, it's a little bit going up and down until this is like all distributed. And that is like pretty constant. And this is just one test, so we did a few. It always comes out the same thing. The only small thing which you might recognize, and we saw that over time, is like a little bit of decrease, and there's a reason for that. So additional things we tried. As I mentioned before, different threading models. The default we went with in the beginning was 9 vertex worker threads. Because at least my idea was you have one JVM, you have 9 worker threads in there. This is better than having 9 JVMs with 1 worker thread. Turns out not so much. So it's interesting. So this is what we talk about. Turns out that this looks better if you go with a single worker thread. Like here, I have a little bit more detail on the data. So you can see one instance can handle more messages per second per thread. Then we tested OpenJ9 versus OpenJDK. So running the same setup again, automated test coming out. So what's the difference? First of all, we had to create an OpenJ9 base image for doing that. We ran the default scenario, and to be fair, we couldn't see any real difference. So does it help? Does it not help? I'm not really sure. Performance-wise, we had the same throughput. If it uses less RAM, maybe, but that was not an issue. So we didn't have a limit, RAM was the limiting factor. But also, to be fair, the performance was the same. So it didn't make any things worse. Quick summary. Yes, it scales. That was what we wanted to find out. Of course, now comes a disclaimer, yes it scales. What does it mean? It scales in the setup that we had. So this is the setup we had available with those 60 machines, and with the setup that we had, we could see that we can scale up until we hit the cluster limit, and in that part it does scale. Question is that good enough? And I had the discussion yesterday, I think. So we had 80,000 messages per second. Is that good enough when you compare that to the cluster that you have? I think there's room for improvement. You can always argue that, yeah, we can have more throughput and we can performance optimize that, and we can go for that. But from a scaling perspective, I think we succeeded. And there's also like a few things that we learned during the test that were actually bugs or issues in Hono, and we fixed that. So you learn things, you improve that, and I would really be looking forward to another test when 0.8 comes out. Probably will be 0.9 or whatever, because it's like a huge amount of time that you invest. So we will continue to improve that and definitely compare that to this test. So, things to consider. The device registry, which is not part of Hono, that might change, has a huge impact on the overall performance. So you definitely need to take that under consideration. The mock device registry helped us for the test.
And sidecarring.
And sidecarring that also helped, but that's definitely not a, I mean, having a mock device registry doesn't work for a productive setup. So that's one thing to consider. And the consumers also play a role in the overall performance. So what we did is we consumed and threw away the data. Now if you want to store that in some database, and this storing process is not fast enough, then the overall system will not perform either. So again, we only had a look at Hono and specific focus on the telemetry data.
Yeah, maybe for the next one we can simulate
the device registry as well.
Device registry and the more realistic consumers, and then try to scale them out as well. So there's a lot of things you can.
Yeah.
You can
but it's like if you have in mind that you store everything in, I don't know, a Kafka cluster, then you need to set up a Kafka cluster as well and test for that and optimize for that and then see how that works. So I would encourage you, try this yourself. Everything is open source.
You only need 16 nodes, it's called.
No problem. With a nice garage. So, any questions?
Just out of curiosity, did you try HTTP2 as well?
No.
Okay, because
No,
it'd be interesting to see if there's a difference.
I'm not sure if this is supported by OpenShift.
Okay.
And Hono doesn't support it.
Yeah.
True, but it could be that you have like the termination of HTTP at the edge of OpenShift. That could be one scenario. And if you cannot pull it through, so if you cannot like push HTTP through the router, so through the OpenShift router, then again this wouldn't make any sense. You can only do this if you use node ports and directly connect the Hono services, then that would work. If Hono had support for that.
But I would, before that, try to test MQTT before, because that's also one of the more realistic IoT scenario.
Device registry also need to scale in such a. How many requests for the device registry you get for one message?
So if the cache doesn't kick in, it's about 2 times the number of requests. So one HTTP request coming in causes 2 requests to the device registry. If the caching doesn't kick in.
It mainly depends on whether your device maintains a connection or a session or not. So with HTTP, with every request you authenticate the device, then authentication takes place every single time. And
so
we have these 2 hits. With
every
MQTT,
connection,
you might get away with fewer hits because if your device maintains a long session, then but I think realistically, the scenario that we designed for to support as well is that the device wakes up, connects, sends data, disconnects, goes to sleep. And with that pattern in mind, with every telemetry that you send, you have to authenticate and will hit the device.
Did you find out from your scenario what was the bottleneck in the end? The Cupid router or
so the bottleneck, what I mentioned before is bottleneck was on CPU and network. So, but CPU was the real limit there, and this was in the Hono services. So I do know that colleagues of us did the scale testing in parallel, testing the messaging layer only. They were available. They were capable of doing more throughput. The problem was the CPU usage on the protocol adapters.
The last question. Since all the Hono adapters were behind the OpenShift router, were you too any limitations of the OpenShift router? Or
Yes.
Like maybe using different size infrastructure?
It was in the slides, but we just skipped over it.
Yeah. So the OpenShift router itself has an impact on performance, a big one. There are many options that you can tweak, but in the end we went with directly connecting the Hono protocol adapters on the node port. this may be possible for you or may not be possible for you. You also might not want to use the OpenShift router in production because you might want to use something like I don't know, F5 or some other cluster load balancer, which takes off the complete load for you. But the default setup of the OpenShift router works quite well for like web stuff and whatever. But it has an impact on